So part 2 of the nucleus, my bad, I lost track of my time and I ran out of my 15 minutes of recording. So we were on this half-life problem where we don't know what our starting amount of uranium is, but we do know how much lead we have after a certain amount of time. So we're going to use that amount of lead and kind of backtrack to figure out how much uranium you started with. So we still have 75 milligrams of the uranium, but we have 18 milligrams of lead. So we've got to proportionally figure out how many grams of uranium created that 18 grams of lead. So the molar mass of uranium is 238. The molar mass of lead is 206. And so just a quick ratio type calculation lets us figure out that a total of 95.8 milligrams of uranium is what was generated, or is what we started with. So now we can go in and solve the equation. Again, here is the version not using the solve function. If you want to use this equation and just go right into your solve function to solve for the time, you can do that. Hopefully in both cases you get 1.59 times 10 to the 9 years. All right, so finishing up our conversation about stability, this is a really interesting visual. When you were in junior high, you probably learned that number of protons and neutrons in the nucleus was equal because you focused just on the smaller atoms like carbon and nitrogen and so forth. So carbon, 6 protons, 6 neutrons. Nitrogen, 7 protons, 7 neutrons. So this straight line right here represents that 1-to-1 relationship. But notice that doesn't hold true for very long. Once you hit about element, what is that, 18, 19 or so, the mass starts increasing much more so than the one-on-one relationship because you're putting more neutrons in there. So this set of black stair steps really represents where the stable nuclei for each of the elements are. And so notice that the bigger the atom gets, the more neutrons we have to put in the nucleus compared to the number of protons, because we need those neutrons to kind of buffer that negative charge. We don't want the electromagnetic repulsion to blow the nucleus apart, so we need more neutrons to allow that to happen. But there's a lot of isotopes of each element that are unstable. So you will notice that the different colors are showing you what kinds of decays the various isotopes are going to naturally undergo. And scientists studying this have developed, have learned that there's a pattern to that. So the stability of the nucleus is controlled by the number of protons and the number of neutrons, as well as the ratio. The belt of stability, which is the black staircase that I pointed out, represents the stable isotopes of each of the elements up through element 82. After element 82, there are no naturally stable isotopes. So uranium, everything's radioactive. Even though you can find uranium on Earth, it's radioactive, so it doesn't get a black dot. It gets a different color dot. So again, as the number of protons increases, we've got to increase neutrons even more in order to keep that repulsion from happening. So you can see if the isotope has more protons than the belt of stability says it should, it's going to cause a beta particle ejection. If it has fewer neutrons than the belt of stability said it should, it will often undergo a positron emission. Now, once in a while, you get a proton or a neutron spit out, but most of the time what you're going to get is either a beta particle or a positron. That is until you start to get a nucleus that's very heavy. So heavy nuclei, you will notice you start to get more alpha particles. That's because by ejecting an alpha particle, you get to step down pretty far. You get to go back down 2 positions on the chart. So that's trying to make the nucleus much smaller. So this is kind of a cool visual that lets you see the stability and the types of decays that are going to happen. So let's look at that a little more closely. So if you have a nuclei with a high neutron to proton ratio, Therefore, it's above the belt. Like we saw, you're going to get a beta particle ejected. Occasionally, it'll get rid of a neutron, but usually it's just a beta particle. And so a beta particle is going to decrease the number of neutrons, but simultaneously increase the number of protons to try and get you to move from left to right on that belt, towards that belt of stability. On the other hand, if you have too low of a neutron to proton ratio, so if you're below the belt in the orange area that we took a look at, that's in the case you have too many protons. So what's going to happen? The proton's going to break down. You're going to get a positron emitted, and the result's going to be fewer protons, more neutrons, so you're stepping up and over towards hopefully a more stable nuclei. Electron capture is something that really doesn't get mentioned very much in AP, so we're not going to worry too much about it. Now, your book mentions it. That's essentially an electron being captured by the nucleus and causing the quarks to rearrange appropriately. And then, like we said, above element number 82, you just have really heavy nuclei, and so they just tend to undergo an alpha decay to try and get rid of a huge amount of mass in one step. So those are the three most common ways of trying to achieve stability of the nucleus. All right, moving on to a couple other reactions. These next three are considered artificial because it's a forced kind of reaction. Now, that's not to say it can't happen naturally. We'll talk about that in a minute. But artificial transmutation is what the scientists were trying to do when they started to see and learn about the nucleus and cause nuclear fusion and fission and what led to atomic bombs and all that kind of stuff. So let's go back to the beginning. If you do something called bombardment, nuclear transmutation, or artificial transformation, what you're really doing is you're shooting a projectile at a target nucleus in hopes that something happens to the nucleus. The result, if something happens, is some sort of particle gets ejected, and then you wind up with a brand new nucleus. So here's an example of one of the earlier ones. This is actually one of Rutherford's experiments. So he took nitrogen-14, shot alpha particles at it, and wound up ejecting a very small hydrogen atom, so one proton, one neutron, and then wound up with a new element. So here's an example of artificial transmutation. So we got the target nucleus is the nitrogen, the projectile is the alpha particle, the ejected particle is the hydrogen nucleus, and then oxygen would be our product nucleus. That's where most of the mass is. So the product nucleus is typically where the mass is. All right, reaction number 3 is fission. This is what takes place inside nuclear reactors. This is what takes place inside atomic bombs. So fission is a bombardment reaction, but instead of having the nucleus just eject a small particle, you essentially blow the nucleus to smithereens. So you wind up with many, many, many fragments, and as a result, a whole lot of energy because you've blown that strong force apart. A lot of energy gets released as a result. So here's a typical example. There's only 2 elements we know of that undergo fission for us. That is uranium and plutonium. Well, naturally undergo uranium and plutonium. In order to accomplish fission, one of the things you'll see is we bombarded uranium with a neutron, but notice that 3 neutrons come out. That's key to allowing these reactions to take place. In addition, look what's happened to the nucleus. We've blown it apart into bigger chunks. So that's fission. So you don't just get one tiny particle out, you blow it into smithereens. Getting more neutrons, getting some gamma rays, getting a whole lot of energy coming out. So, yep, that's what happens. A scientist named Meitner was able to calculate the energy released during a nuclear split and realize that there's a whole lot of energy coming out. She was also able to determine that because neutrons are generated in greater number than it took to split the uranium, you can cause something called a chain reaction. And this is why you get so much energy out. So one neutron causes a uranium to split, but then that uranium could go on to split many more, and many more, and many more, and so on and so on. And so where does all that energy come from? The energy of an atomic bomb. Where does all that come from? Well, part of it is the strong force. You've held all of those particles together inside the nucleus for a really long time. You blow it apart, and you release a whole lot of energy as a result of that. Also, Einstein's relativity theory comes into play. E equals mc squared. E, energy gets released because a little bit of mass gets converted into a whole lot of energy. And so there's the other idea. All right, so the last reaction is fusion. Fusion, we're taking smaller nuclei, combining them into larger, much more stable. This is what happens in a hydrogen bomb, and this is what happens actually on the sun. The reason why we've got all the energy we do from the sun is because of fusion reactions going on there. So here's two typical reactions. You take hydrogen and fuse them together to make helium and wind up giving off a whole lot of energy as a result. Notice that this is not alpha, this is helium. There's not really radioactive particles giving off. So the nice thing is with fusion, there's very little radioactive fallout. Plus, since it's hydrogen, we have a huge source of hydrogen in all of our oceans. So there is a big push to try and get fusion to take place in a very room condition situation so that we could harness that energy and use it. The problem is the temperature that you need to get this reaction to happen right now is so high, it takes more energy to maintain that temperature than you get energy out from the fusion reaction itself. So fusion reactors, if we could ever get fusion to occur at cooler temperatures, would be an awesome source of energy. But that's the fourth type of nuclear reaction. So we've covered the nucleus, probably more than AP is going to need you to, but it's good to have a little bit of that information. So half-life, you very well may see on AP. The stability of the nucleus once in a while will come into play there, but I think knowing some of these other reactions couldn't hurt as well. All right, so you got problem sets to work on now.